We're going to review for our final exam. Now, this is a cumulative exam, which means it's everything we've covered for the entire semester. I can't go over that in this review. So there are also other reviews on Canvas. Every day, you'll just be doing a different review on Canvas, just to give you lots of practice and to help you space it out. Okay. You'll notice today, I'm going to ask you a lot of questions for every topic because you don't know what will show up on the test. Now, not every question will be this in-depth on the test because that would just take you too much time. Okay? But you can expect at least this many questions, probably a few more, okay? Because it is a cumulative final, it is pretty long, okay? But each question will be a bit shorter than what we have here. Okay? But anything on any of these questions could show up on the final, just not all of it. So in this example, we have tennis players often spin a tennis racket and observe whether it lands with the logo facing up or down to determine who serves first. But is this really a 50-50 process, equally likely to land with the logo facing up or down? To investigate this, a tennis player spun his racket 100 times, and he obtained 46 up and 54 down results. Does this provide much evidence against believing that spinning the racket is really a fair 50-50 process? So first of all, I wanted to show you when you come to Canvas and you come down here to study for exams, I've now uploaded our final exam formula sheet. And let me show you what that looks like. So this is the formula sheet. Basically, I want you to print this off and keep it with you for the next couple weeks while you study. Every time you do any homework, any of the reviews, anytime you're doing any studying, have this next to you. Okay, get used to using this, not your notes, to try and get your hints. You want to be very familiar with this when you get to the final. So, just to point out quickly, there are some questions you can ask yourself first. You have your standardized statistic and your confidence interval. Okay, but then basically, if you have one sample, you can either look at one proportion or one mean. Okay, if you're comparing two groups or comparing two samples, comparing two populations, you can either do two proportions or two means. Okay. And then the other thing we've learned how to do is to decide if two variables are associated. And that can be a chi-square test if they're both categorical, or if they're both quantitative, that's going to be regression. Okay. So basically there's 6 big things we've learned how to do. Okay. We've learned how to do one mean, okay, one mean or one proportion, two means or two proportions if we want to compare our two groups. And then if we want to see if two variables are related, we learned how to do regression, and we learned how to do chi-square tests. And so 6 large things. Now, coming back to this, when you read a problem, ask yourself, which of those 6 big things is it asking me to do? Okay, do I have one mean, two means, one proportion, two proportions? Am I doing chi-square or regression? Okay, figuring out how to tell which one you're doing is going to help you a lot. So when I look at this, I'm only seeing one variable. It's just whether or not it's up or down. So my variable is whether the racket is up or down. Okay, that is categorical. And specifically, it's binary. There's only 2 responses, up or down. Okay, once I know that it's categorical, I can go back to my final exam formula sheet and I want to ask myself, how many variables do I have? I only have one categorical variable. If I only have one categorical variable, then I have to be dealing with one proportion. Okay, there's no other options. That's the only thing that has only one proportion or one categorical variable. Okay? And then you can look and say, oh, well, here's my descriptive statistics and everything else that follows for one proportion. Okay, so we're going to be doing one proportion. And knowing that is going to help me do this entire problem. Let's just move it up here to the top of our problem. So now let's produce a graph. What kind of graph to use for one proportion? Coming back to the formula sheet, for one proportion, you're going to want to use a bar graph. And a bar graph, pretty simple. We would say up, down. How many times did we get up? We were up 46 times, so you draw a nice bar. How many times were we down? Well, 54 times. So you draw the bar like that, and you're like, oh, well, we were up less than we were down. Very simple to look at. You could also do a 0.46 and 0.54. You could do it as proportions, or you might have it as percentages, 54%, 46%. Any of those options would be fine. It could show up like that on the test with any of those options. Now let's identify our statistic and what would be an appropriate symbol. So what do we use to summarize one proportion? For one proportion, you look at the sample proportion, which is p hat, and we'll do p hat equals 0.46. We're going to look at how many times we spun up. Could someone have chosen to do how many times it spun down? Sure, but we're going to look at the times it was up. So the proportion that landed up is 0.46. Now, let's define what the parameter would be in words. So remember, statistics are for samples. So statistics are samples. And parameters are for populations. We can remember that because samples start with S, statistics start with S. Population starts with P, parameter starts with P. So our parameter of interest would be the proportion, or I was going to say the proportion of the population, but it might make more sense to say the long run proportion, or like population proportion, of times the racket lands face up is point. We don't actually know what it is. We only have a sample. So we don't know what it will be, but we can use the symbol pi here. Okay, so that's our long run proportion of times it lands face up. But we don't actually know how often it lands face up in the long run. Now, let's say our null and alternative hypotheses that we could use for this research question. So if you remember, what did they want us to compare it to? They want to say, is it really fair? Is it really a 50-50? So, in words first, our null is that the long run proportion, so the long run proportion of landing up is what? Okay, so remember, our null always has to be an equals. Is always the boring thing, or like assuming that everything is true. So that in this case, it would be that it is 50%, or 0.5. The alternative is what we kind of are hoping to show. So sometimes they're hoping to show that it's less than or greater than. Sometimes we just want to know if it's different. If you read this again carefully, I don't think it says anything of we suspect it is going to be less than 50% up or more than 50% up. I think they just want to know, is it not 50%? So our alternative will just be that the long run proportion of landing up is not 0.5. If I want to do it in symbols, it would look like this. So my null, which we use with a little 0, would be that my population proportion, we use the pi symbol for that, equals 0.5. So again, your null will always be in equals. That will help you figure it out. Okay, and my alternative will be that pi is not equal to 0.5. Also, make sure that your hypotheses are always about parameters, never the sample statistics. So always population parameters, never about the samples. So if you see a p hat in there, you know it's going to be the wrong choice. Let's see, what would it actually mean to us to have a 0.5 probability of the racket being up? Like, what would that actually be? So we've talked about probability as long run proportions. So a 0.5 probability means that if we spun the racket thousands of times, okay, it would land up about 50% of the time. That's what a 0.5 probability would mean, or about 0.5 of the time if you want to keep it as a decimal. Now let's describe how we could use a coin to conduct a simulation analysis of a study and its results. And we want to go into lots of detail. This is copied from an old review that the professor that writes the exam had. Okay. And so she's telling you have lots of detail and talk about how you decide if the observed data gives you evidence against believing that spinning the racket is really a fair 50-50 process. So basically what we would do is we could flip a coin blank times. Okay, well, remember we spun the racket 100 times, so we want to flip the coin 100 times and find the proportion of times that we got a heads. This represents how many times we need to get the racket up in 100 spins. Okay, but that would just be one repetition. So basically, we need to repeat this at least 1,000 times. Okay, so our textbook always says 1,000 times, but remember, there's a lot of variation in the simulation from person to person. Like if you do 1,000 times and I do it 1,000 times, we might get very different p-values. So I like to do at least 10,000 times unless my applet's too slow, just because then you're more likely to get the same answer that I got. Okay. And then after we've done this 1,000 times, we're going to find the proportion of times that we got results as extreme as our statistic. So for everything we have done in this entire semester, our p-value is always the proportion of times that we got results as extreme as our statistic. And our statistic in this case is 0.46. So we would just look at how many times did we get a sample proportion as extreme as 0.46. And let's show you what that actually looked like on these null distributions. So one of the things she might do on the final is she might give you a couple different graphs and say which one could actually be our null distribution. And that comes down to, do you remember where the null distribution should be centered? Okay. If you don't, come back to your formula sheet and say, oh, my null distribution, the mean or the center should be at pi, whatever we're proposing for a value of pi. So the mean of all those sample proportions should be at pi. So it should be centered at pi equals 0.5. Remember, our null hypothesis was that pi equals 0.5. So see which one of these is centered at 0.5. So this one looks like it's centered. Yeah, that's probably about 0.5. This one's centered at 0.46. So it can't be that one. It's going to be centered at pi, which is 0.5, not at your sample proportion. Okay. So the null distribution always assumes the null is true. Let's make a note of that for ourselves. So the null distribution always assumes the null hypothesis is true. That's why it's called the null distribution. So we know that one can't be our null distribution. So this is our null distribution right here. Okay. So what we would do, once we know that that's our null distribution, we would find the proportion of times that we got our sample of 0.46 or something more extreme. So I find 0.46, which is probably, these lines are a little bit difficult to see where it is. Let's say this is 0.46. And then what would be more extreme? It would be anything to the left, right? Or 0.46 is about like 0.4 away from 0.5. If I went to 0.54, so like right about here, and I found everything to the right. Now, you don't have to figure that out. We just use the applet. Okay. But basically, you need to know that you're going to be looking at both tails. Okay. Once I look at this, does this seem like 0.5 is a plausible value? Does it seem pretty likely that I could get 0.46 or less, or 0.54 or more when my true proportion is 0.5? Seems very plausible. This is a very big p-value. Even without knowing the p-value, I can tell you looking at that area, it's going to be very big. So just by looking at the null distribution, the p-value is going to be very big. So 0.5 is a plausible value. So if 0.5 is a plausible value, then would you have convincing evidence against the belief that spinning the racket this way is a fair 50-50 process? We would say no. With a big p-value, we do not have evidence that the long-run proportion is not 0.5. So remember, we can always check to see if our null is plausible, but our conclusion is always in terms of the alternative, and the alternative was that the long run proportion is not 0.5. So we're like, no, we don't have evidence that the long run proportion is not 0.5. So here's a different question though. Based on those results, we said we don't have evidence that the long proportion is not 0.5. But could you say that the probability is 0.5? Okay. You have to be very careful with this. Okay. So we can't say that we have evidence for the null. Okay. We are always looking for evidence against the null. So what that means is we didn't find evidence that the proportion is not 0.5, but that doesn't mean that we can say that it is 0.5, okay? 0.5 is just plausible, not that, but we could still be wrong. So we don't like to say, oh, like, we've done all this, we know it's 0.5. Well, maybe it's 0.5, but maybe it's also 0.51 or 0.49. Who knows exactly what it is? We didn't have any evidence that it's not 0.5. 0.5 is still plausible. Okay. Could you generalize this to all tennis rackets? Well, was this a random sample of all tennis rackets? No, if you go back up and look, this was not a random sample from all tennis rackets. They only spun one racket. So we can only talk about this one racket. Maybe different brands are different. Maybe we did something to break this one. Okay. We can't say anything about any other rackets because we only spun one racket. So we can only talk about this one racket. Okay. Now, what applet would we want to use to find the simulated p-value? Well, coming back to your formula sheet, it will even tell you that. Okay. On the formula sheet, if you want a simulation, we need to use our one proportion applet. Okay, so we use our one proportion applet to find the simulated p-value. When you put it in, this will always be what you have in your null. So we put 0.5 as our probability of heads. Okay. Our number of tosses is your sample size, n, your sample size. And then this is your number of repetitions. I like to put in at least 10,000. Okay. And you draw your samples, and it will put in all of your samples here. So each of these is different proportions that you could get. Okay. But I said that, let's actually look over here first. Okay. So we're looking at the proportion of heads. Okay, these are all the different proportions of heads I could get in my different samples. So these are my different samples. Or my different sample p-hats. Okay. And then once we do that, we want to count our samples as extreme as our 0.46. Now this applet is different than every other applet we did because if you want two-sided, you actually have to click this two-sided. Okay. So we put in 0.46 and then we click we want to do two-sided. As you don't have to change anything else in there, just click the two-sided. Okay. And then, again, this is different than every other applet because it puts your p-value up here. So this is our simulation p-value. And again, you can see that it is pretty big. So to interpret the p-value, that means that if the null is true, it should always start with if the null is true. So if the population proportion really is 0.5, then there was a 0.49 chance of getting our sample statistic of 0.46. It's unfortunate, those are so close together. We'll say our sample statistic of p-hat, I can't actually type the symbol, of 0.46 or more extreme. So remember, your p-value is always saying if the null is true. then this is your chance of getting your sample statistic or something more extreme. Now, I wanted to show you, I don't know if it would come up on the final. I feel like by the time we get to the final, we've forgotten counts and using the numbers, but I just didn't want to show you quickly. Okay, remember back in chapter 2, we said we could look at the proportion of heads, or we could typically just look at the count, the number of heads. Okay. And so if you look over here, it's just, these are the number of heads. It would actually be centered at 50 heads because that's what you would expect if the null was true. Okay. And then they looked for less than 46 heads or more than 54 heads. But notice the p-value is exactly the same. Okay. So it doesn't matter if you do counts or proportions, except for what number you put in here. If you want to do 0.46, you need to have proportion because 0.46 is a proportion, not a count. Okay. I believe on the final, I would be very surprised if she did anything with counts. So it'll probably be proportions, but I want you to remember that you have to click the button for the proportion of heads. Okay. Now, let's find the standardized statistic and interpret it. Okay. So do you remember how to find a standardized statistic? If you go to your formula sheet, we have one formula that's working for almost everything we do in this class. Okay. There are different formulas for chi-squared and regression, but we don't actually ever have to do that by hand. So basically, if you are asked to find the standardized statistic, it's going to be this Z formula. Okay. I highly suggest always writing out the formula every time for anything you do, just because it helps you memorize it. So Z is going to be equal to our statistic minus the mean of the null distribution over the SD of the null distribution. And how do you find those numbers? You just read them off the chart. Oh, but before you can read them off the chart, I have to actually click this button right here, which I did not do. So let me go find those in the applet. So if I put everything into the applet like we had, notice it will tell you right here what your mean and SD are. This is just pure coincidence. The right here, they are both, oh, the mean is 0.5, the SD is 0.05. I was going to say they're the same, but they're not if you look closely. So I should have said on the applet that the mean equals 0.5 and the SD equals 0.05. And so you just read them straight off the applet. So our statistic was 0.46, our p hat, then minus the mean of the null distribution, which is 0.5, divided by the SD of the null distribution, which is 0.05. And that should tell you 0.46 minus 0.5 divided by 0.05, negative 0.8. Now, I want you to notice, if we clicked this button for normal approximation on our applet, it will tell you your Z value. There's your Z value right there. Okay. And that is your theory p-value. Sometimes the Z that they give you, it is based on the formulas and not the simulation. So sometimes it will be off by a little bit. But on a multiple choice test, it would get you close enough that you could get the right answer. However, it is possible she would only give you the simulation. She'd only give you this part right here, and she wouldn't give you any of the other numbers. And so it is good to be able to do it by hand, just given the simulation. Okay. But you have the ability in a lot of situations, even if she gave you part of it, you can pull up the applet yourself. You could try and put it in and try and find the Z value to double check your work. So practicing it by hand, but this is a way to double check your work. Okay. But there could be situations where, again, she only gives you the simulation and you don't know all the information to do it yourself. So you do need to be able to do it by hand by just reading the mean and SD off the simulation. And how would you interpret it? Your standardized statistic is how many standard deviations you are from the mean. So our statistic of 0.46 is negative 0.8, or we could say 0.8 standard deviations below, because it was negative, so we say below the mean, or we could say below the hypothesized value of 0.5. Okay, so you might see it written as just below the mean. You might see it written out as like below the hypothesized value of 0.5. Either one of those could be correct. So maybe we'll say 0.8 SDs below the hypothesized value of 0.5. Okay, now on this problem, were the validity conditions met to use a theory-based approach? Well, for one proportion, you can come back to your formula sheet and it will tell you your validity conditions right here. We need at least 10 successes and at least 10 failures in the sample. So we need at least 10 successes and 10 failures. Okay. In our case, we had 46 up and 54 down. Okay. Those numbers are both over 10. So, yep, we're good to go. We can use the theory base. So if we want to use the theory base, there are sometimes more than one way you can do it. Okay. So in the one proportion applet, you could click this normal approximation and it will give you your theory base p-value. Okay. Or we can use the theory based inference, the TBI applet. Okay. On the final, she likes to always write TBI because she doesn't want to write it all out, but that's the theory-based inference. So we'll use the TBI applet to find the theory-based p-value. So you put it in, you have to check move, or use this drop-down to say we're doing one proportion. Your sample size is 100, your count of heads up was 46, and your sample proportion, it will calculate this as 0.46. But if you don't know your count, you can put in 0.46 and then it will figure out the count for you. So whichever one you know, you just put it in here. Click calculate. Notice it'll give you your nice bar graph. Okay. You do have to say, okay, I'm comparing it to 0.5, and you have to say it's a not equal to. Okay. Once you do that, your standardized statistic, z is -0.8. There's your theory-based p-value. And you can even ask for a confidence level. So I asked for 90%, but you could ask for 95%, 99%, and it'll give you your theory-based confidence interval. So this is what the null distribution should look like using the theory. But let's practice using our formulas to predict what it should look like, because she could also tell you that instead, ask you that instead. So let's remind ourselves again of what is a null distribution. The null distribution is all the possible sample proportions we could get from different samples if the null hypothesis is true. Okay. So the null distribution, we assume the null is true, and then here's all the different possible sample proportions we could get from different samples. Okay. What would the shape of that null distribution be? Well, if you look back up when we simulated, you'll notice it looks pretty normal. If you look at the theory base, they told you, oh, it should look pretty normal, right? And if you remember, what was it that told us it's always going to be normal? It was the central limit theorem. Okay, and so the central limit theorem says the proportions, or the possible sample proportions, look normal, okay, if the sample size is large enough. Meaning at least 10 successes and 10 failures for proportions. Okay. And in this case, yep, we have a large enough sample size and our shape was normal. What about the mean? What do we predict the mean would be? So you come back to your formula sheet and you're like, oh, well, the mean should just be equal to pi. So the mean of the p hats should just be equal to pi, so 0.5. And the SD, so the SD of the p hats, which in our book, we use the notation SD of p hat. That means the SD of the p hats. Okay. And that should be equal to this pi, so the SD of p hat should be equal to pi times 1 minus pi over n, inside a square root. So it's going to be equal to pi, not p, times 1 minus pi over n. So it's going to be 0.5 times 1 minus 0.5 over n, which is 100. And if you put that in your calculator, you should get 0.05. This is how we could do it by hand. Now, coming back up to your simulation, those are the numbers I got right here, okay, when I click summary statistics. So if you panic on the test, go put it into the simulation. See what mean and SD you got. Actually find the null distribution and give her the answer that way. Okay, but let's also practice doing it by hand, using the formulas. But if you panic on a test, or if you want to double check your answer, you can still go use a simulation and figure out the same answer. Okay. Let's see, what is the theory-based 90% confidence interval? So I put in 90% and it gives me my confidence interval. So it's 0.378 to 0.542. Okay. And now we want to interpret it. Okay, so there's the bare bones interpretation, which is we are 95% confident that the population proportion is between 0.378 and 0.542. So that's the bare bones. You could also put it in context. So you could say something like, we are 95% confident that the long run probability of the rocket landing up is between 0.378 and 0.542. Now, what would happen to the width of the interval if we use 95% instead? So when you get to these pictures, I always want you to pause, draw out something like this. Okay, so if this is 90%, how do we go to 95%? You have to make it wider. So 95% will always be wider than 90%. But sometimes, like, you'll start at 95%, she'll say, well, what about 90%? And so draw out the picture and then figure out the answer. So in this case, if we use 95% instead of 90%, it would be wider. The only way we get more confident is to make our interval wider. Okay. What would happen to the width of the interval if we used a sample size of 50 instead, but our sample proportion was still 0.46? So it's saying nothing else changed, but we just changed our sample size. So let's think about this. If we started with 100, and then we want to see what 50 would be. Well, bigger sample sizes mean narrower intervals. That's the part that I remembered. So I remembered bigger sample sizes mean narrower intervals. They also mean smaller p-values. It just means we're being more accurate. So if bigger sample sizes is narrower, then the opposite must be true. If I want to do 50, it's going to be wider. Okay. So 50 will be wider, because bigger sample sizes are narrower, so if you go to smaller sample size, it would be wider. Okay, now let's suppose that you panicked on the test. Okay, let's pull up our theory-based inference and put it in. So we could put in 100 for the sample size, we could put in 0.46 for the sample proportion, we can click calculate, confidence interval. So we had 90%, and if you want to know what happens when you go to 95%, put in 95% and calculate it, okay? Or let's say we're still at our 90%, so there's my 90% confidence interval. What happens if my sample size was only 50? I can actually just change it and say, well, what does happen? Okay. Oh, look, it got wider. Those numbers are wider. Again, learn everything to do it by hand, but to double check yourself, you can do a lot of this in the interval, in the applets. Let's see, what would have happened to our p-value if we use, so not the constant rules anymore, but the p-value, if we use the sample size of 500 instead of 100, but the sample proportion was still 0.46. Well, we know that bigger sample sizes are more accurate, and that always means smaller p-values. Okay, so we'd get a smaller p-value. If you're not sure, come back, do your test of significance. You needed a two-sided. There's my sample size of 100. Okay, and you can see what the p-value is like 0.0. I guess this won't help you very much if you're already at 0. But then you could put in 500. You'd have to change the count and make your sample proportion. Okay, you're going to have to just reset it and start. But you could put it in and do it all. So you do 500, you put in 0.46 for the sample proportion, calculate, and it will give you your p-value. Oh, I must have had something in there wrong. Okay, so our p-value before, sorry, it said 0, but I don't know what was in there. Our p-value before, if you remember, was actually like 0.4. So now it's all the way down to 0.07. So you can double check yourself that way. Okay. What would have happened to our p-value if we had a sample size of 100, but a p-hat of 0.3? Well, let's think about this logically. We know our null distribution should be centered at 0.5. We got 0.46 originally, but what would have happened if our p-hat was 0.3? So then, if we filled in the tables, it would have been much smaller, right? If we're farther out in the tails, we get smaller p-values. So statistics, farther in the tails, means smaller p-values. Okay, next example. We have the data for the length of a word, each word in one song by Beyonce built into the applet. Now, looking at this, before I do anything else, okay, what would your variables probably be? Okay, are we looking at like one mean, one proportion? Length is numerical. So that would be quantitative. Okay. Do you see any other variables? I don't see any other variables. I think we just have one variable. Length is quantitative. So we're going to be looking at one mean. So everything we do is going to be for one mean here. This is a dot plot. Okay, so each of those dots represents the length of one word in this song. If I was to describe the data, I want to describe three things, or four things possibly. The center, spread, shape, and if there's any unusual observations. So the center, where do you think this is centered at? I would probably say it's centered at maybe like 3 to 4. Okay. The spread looks like we go from 1 to 7 with maybe an unusual, like maybe an outlier at 10. Or it looks like 2 outliers, because there's 2 dots. That's just like a general spread. We're going to measure it more precisely with our standard deviation in a minute. What about the shape? Notice how it kind of has more of a long right tail, or you have this unusual observations. I would say this one is skewed to the right. So that's the long right tail. And again, 2 unusual observations at 10. So unusual observations, we're like, oh, it's just far away from the rest. If it's really far away from the rest, we might even call it an outlier. But we also mostly just use those 2 words interchangeably. Now, if I told you that the median is 3, can you guess the mean? This comes back to a theory base of, if we start with a symmetric distribution, then your mean and median will be about the same when it's symmetric. But if you have a skewed right distribution, which one of those 2 gets pulled up by the long tail? If you remember, your median doesn't change very much. It will change a bit, but not as much. So if your median is there, your mean will get pulled over. So this will be your mean. So the mean is always pulled by the long tail or unusual observations. Or it's pulled a lot more. So the mean is pulled much more by the long right tail and unusual observations. Okay, so the mean must be bigger in this situation. So I'm going to guess, I mean, looking at it as kind of the tipping point, I'm going to guess like 3.5 or 4 maybe. Okay, I just know it has to be bigger than the median. What about, do you think that the standard deviation is close to 0.5, 1.5, or 3? We're never going to ask you to calculate it by hand, but this does come back to one of the most important foundations in this entire class, but not one we actually talk about for the last little bit, is remember our empirical rule that said if you have it was talking about symmetric data, but it will work well enough for most data sets. If you have a symmetric data set and you say, here's your average or the mean, and you go out 2 standard deviations in either direction. Okay. So you find your average and then you go out 2 standard deviations in either direction. That should be about 95% of all of the data. Okay. So let's write that. So 95% of the data should be within 2 standard deviations of the average. Now, again, that works the best for symmetric data sets, but it will still help us estimate here, that rule. So coming back up, if we are guessing that our average is about here of like 3.5, and if I go this far, that should be 2 standard deviations. Okay, so how far is that? That's like from 1 to 3.5. So if I think that my SD is 0.5, that means that I should start at 3.5 and go 2 in each direction. That would be, sorry, if I go 2 standard deviations and it's 0.5, that would be like only 1. Okay, so this would be like 2.5 to 4.5. Is that 95% of my data? Okay, no, it can't be that one because my data goes from like 1 up to 7, so it can't be that. Well, let's try if I'm at 3.5 and I go 2 times 1.5, or 2 times, that would be 3. So that put me up to like 6.5. And if I go this way, that would put me down to 0.5. So it's about 95% of your data from 0.5 to 6.5. 0.5, 6.5. Yeah, that's about 95% of my data. So I think it must be 1.5, because that's the value where if I got 2 standard deviations in either direction, that's going to be most of my data. I don't think that's something that'll be on this test, but it is something she loved to put on the test in the last class before we got a new textbook. So you never know. Okay, but just remember, 95% of the data should be within about 2 standard deviations, so you can kind of eliminate the choices that must be wrong. Let's see. We could also separate our words based on whether or not they have the letter E in them. So in our descriptive statistics applet, I pasted in all of the data and I clicked use data. Okay. And I had to change the quantitative variable to length because it was trying to do something different. And then I separated it by the variable of whether or not it has the letter E. Okay. And I've asked for the actual mean and standard deviation. And you can look at dot plots or histograms here. Okay. And so these are your 2 groups for the ones that don't have the letter E and the ones that do have the letter E. So let's start by comparing the centers. So the centers is look at the means. So it looks like the words with the yes has a slightly higher center. Now let's look at the spread. So we compared the means. If we want to compare the spreads, we could compare the standard deviations. Okay. So looking at it, my standard deviation is 1.7 or my standard deviation is 1.5. So it looks like, again, yes has a slightly higher spread. Okay. So we use the means and SDs. We could also use the medians and the interquartile ranges, and we'll talk about those again later in this book. But we chose to use the means and SDs because that's what I displayed for you. Okay, so now let's look at this one. Because we have every word in the song, we can think of it as the population because we have all the data for that song. So here's your population data. The population mean, we use the symbol mu equals 3.586. And for our population standard deviation, that's the symbol sigma, so 1.604. And our population size, we don't usually ever care about the population size. Now that's our actual population because we had every word in the song. Now suppose we want to take a sample of 50 words from the song and look at the sample mean. The sampling distribution will be the set of all the possible sample means I could get from different samples from this population. So let's use our central limit theorem to predict the following for the sampling distribution. So our shape, the central limit theorem says that, let's see, all the possible sample means will be normal if the sample size is at least 30 for means, okay? Or at least 20 if the population was symmetric. Okay. In our case, okay, our sample size of 50 is going to be more than 30, so we will be normal. Okay. You'll notice when you look at the final exam formula sheet for one mean, so now we're looking over here, it just says you need a symmetric population or the sample size of at least 20 and the sample not too skewed. That's for a t-test. It's a little bit different than just the central limit theorem because the t-test gives you a little bit more wiggle room. Okay, but that's the only thing that'll show up on here. But really, if you just remember, if your sample size is at least like 20, you'll be okay. And then we know that our mean of our sample means, our sample mean is x bar. So sample mean, that'll be x bar. So our mean of all of those, you come back here to your null distribution, the mean will be equal to your population mean, mu. So in this case, we know our population mean is 3.586. So our sample mean should all be centered at the population mean. That makes sense. Right? And the SD of our x bars, or we can use the notation SD of x bar for this textbook, that is equal to, come back to your formula sheet, the SD of x bar is a sigma over the square root of n. So sigma is your population standard deviation, so the 1.604 divided by the square root of 50 should give me 1.604 divided by the square root of 50. So 0.2268. Now, we're going to use the one mean applet to take 10,000 samples of size 50 and to see if the simulated distribution matches our theoretical results. Now, the problem with doing one mean is it's the only thing we learned in this class that the simulations are kind of tricky for, because the simulation, you actually have to have the population data. And we're almost never going to have the population data. So doing this by hand on the test, you definitely have to know how to do it by hand, because you're not going to have the population data on the test. So you can't actually check yourself with the simulation for one mean. Okay, but this is a random situation where I actually have the population data. So I put in my population data. So there's your population data. And then I click show sampling options. I want 10,000 samples. My sample size is 50. Okay. You can see this is my most recent sample. This was my sample mean from one sample. And you can see how it puts the little dots and be like, these are the people we pulled out for our sample. Okay. My choose statistic, I'm just looking at the mean. So these are all of my sample means. It rescaled it. Okay, but if you look at the actual scale from 3 to 4.2, you'll notice that would have only fit in from like here to here. So they have to rescale so you can actually see the shape. But our sample means always have much less variability than the original population. Okay. Notice when you look at the standard deviation of our sample means, 0.22, that's a lot smaller than the standard deviation of the entire population. And that's just always the way it is. So let's just check these numbers. So what we had, our mean of 3.587. Yep, that's about what I expected. Simulations are always off a little bit. My SD is 0.229, and I had predicted 0.2268. Very close, perfect, it's a simulation. And my shape looks normal. Okay, so everything, the mean, SD, and the fact that it was normal, they all matched what the theory said it should be. Okay. Now, there is a caveat. If you're reading through all your texts, all your notes or the textbook, you might see the thing that says, oh, our standard deviation formula is only accurate if the population is at least 20 times larger than the sample. Now, usually anything we're interested in, the population is that much larger. And so it never comes up and we never talk about it. In this case, we actually had a pretty small population, so I pushed this button to make the population size bigger, but that was just so that it worked. Okay. I don't think that's something that would come up, but I wanted you to be familiar with it as you're reading your notes so you weren't confused. So now let's look at our next example. We want to estimate the mean sleeping time of all students at a specific university. From a random sample of 30 students, we found a sample mean of 6.46 hours with a standard deviation of 1.51 hours. When you look at this, write down the information they tell you. Like, so your random sample is 30, so write down my sample size is 30. We found a sample mean, that's x bar equals 6.46. Okay. And my standard deviation, that's S, my sample standard deviation of 1.51. Having that will help you know, oh, we must be talking about means, okay? And I only see one sample mean, so this must be a one mean problem. And let's see, up here again, we want to estimate the mean sleeping time of all students at a specific university. So it looks like my only variable is sleeping time. And that's quantitative. And that's my only variable. So you come back to your formula sheet and you're like, oh, the only thing that has one quantitative variable is this one mean. And so you know what formulas you're looking at. Now, this says use the simulation results to find a 2 SD confidence interval for the population mean. There's not really a way for you to do the applet without the population data, okay? But she might give you this. It's very likely that there will be at least one problem where she says, here's this distribution. Now find a confidence interval, or here's a distribution. Do something with it, okay? So she gave us the distribution. You can see that we had the mean and SD. So these are the mean and SD for our distribution of our possible statistics. Okay. Let's find a 2 SD confidence interval. Looking at the formula sheet, okay, we have the 2 SD method is the statistic plus or minus 2 times the SD of the statistic. Now the SD of the statistic can be read off the simulated distribution on the applet or estimated with the SD formula. Okay, so let's practice reading off the distribution first. So this is my distribution from my applet. This was my sampling distribution of all the different possible sample means I could get. So my formula is my statistic plus or minus the SD of the statistic. Okay. And what is our statistic? Our statistic was our sample mean of 6.46. That was my actual statistic. Then we look at the SD of all my sample means. So here's all my sample means. Okay. And the SD of my sample means is 0.275. Sorry, I skipped the whole 2 part. Don't forget that on your test. 2 times the SD of the statistic. So 2 times 0.275. So 0.646 minus 2 times 0.275 equals 0.096. 2. And now I do 0.646 plus 2 times 0.275. Oh, you know what? I typed this in my calculator wrong. I was wondering why that number was so small. Okay, it should be 5.912, and if I do the plus, I get 7.01. Okay. So that's my confidence interval when I simulated it. Okay. Now, suppose I didn't give you that simulation. We have formulas that you can use to find it without using the simulation. Okay. So it's still going to be our statistic plus or minus 2 times the standard deviation of the statistic. Okay, and my statistic is still going to be 6.46 plus or minus 2. But now, instead of my standard deviation of the statistic, if I don't have that simulation, I can use the SE formula. So sometimes I don't have that, and we go use the SE formula. So come to your final exam formula sheet. There's only one thing on here for one means that says SE, or standard error, so it must be this one. So it's going to be S over the square root of N. So S over the square root of N. So S is my sample standard deviation of 1.51. My sample size is 30. And so I just plug those in. That's how I'm going to estimate what the standard deviation of that statistic should have been. So we'll do 6.46 minus, actually, let's do it in 2 steps. So let's do 6.46 plus or minus, let's do the 2 times 1.51 divided by the square root of 30. So 6.46 plus or minus 0.55. So we'll do 0.646 minus 0.55. Oh, you have to actually put it in your calculator, correct? So we get 5.91 to 7.01. Okay, so again, if you have the simulation, you just get to read the ST straight off of it. If you don't have the simulation, you have to use the SC formula to estimate it. Now, how would we interpret this? We would say something like, we are 95% confident that the population mean sleeping time is between 5.91 hours and 7.01 hours. Now, where was the center of this distribution? So the center is at 6.46, our sample mean. And it will always just be centered at your sample statistics. So whatever that was your sample mean or sample proportion, that's always your center. What was the margin of error? That's the part that you add or subtract. So in our case, we were adding or subtracting our 0.55. So that's our margin of error. Now, let's use our theory-based inference applet to find the 95% confidence interval for the population mean. Before I actually put it in, were the validity conditions met? Okay. The validity conditions say you need a symmetric population or a sample size of at least 20 and the sample's not too skewed. Well, in this case, I don't know my sample, but my sample size was over 20, so we're good enough. Okay. We go into our scenario and we say it's one mean. Okay, we put in our sample size, mean, our SD, click calculate. Okay. Click this confidence interval. I want 95% confidence interval, and here's your confidence interval. Notice it is slightly different. Part of that is because it is theory-based, and part of it is also because they don't have to round. Okay, but the theory-based will be off just a tiny bit. Okay. Now let's see, based on just the confidence interval, would you have evidence that all students in the university sleep less than 7 hours a night? Okay. Well, if you look at it, it's 7 in that interval. So looking at this interval, 7 is in the interval. Okay. Let's see. So if 7 is in the interval is all of your plausible values. So 7 is a plausible value for the population proportion. Okay, so that means we do not have evidence that the population proportion, oh, I said proportion, I don't mean proportion, I mean mean, which is unfortunate. They should have a different word for that than mean. It's confusing, so many different meanings. So 7 is a plausible value for the population mean. So we do not have evidence that the population mean is less than 7. Okay. Now, if this entire interval had been less than 7, which it almost was, but if the entire interval had been less than 7, we'd be like, oh yes, we have evidence that the population mean is less than 7, because the whole interval is less than 7. So all the plausible values were less than 7. Okay. What would happen to the width if we used 99% instead? So 95% would look like this, and 99% would have to be wider. So the only way you get more confident is to make it wider. And what would happen to the width if our sample size had been 300? So to go from 30 to 300, we know that bigger sample sizes make narrower confidence intervals. So if we were to draw our picture, we started at 30. Oh, I need to start the other way. We started at 30. If I did 300 instead, it's going to be much narrower. Okay, one more here today. Someone at a different university, so new data set, thinks the students at the university sleep less than 7 hours a night. Okay, so their thinking is probably less than 7 hours a night. A random sample of 50 students, so that would be my sample size, at this university gave a sample mean, so that would be X bar, and a sample standard deviation of 1.1. On the final, please take scratch paper, write all these things out, write down these symbols. It will help you so much if you have these written out with the correct symbols. Okay, and we want to know, is the sleep less than 7 hours a night? So sleep less than 7. That's the thing that we're interested in knowing. Now looking at this, how many groups do you have? Looks like we only have one group. It didn't mention multiple samples. Okay, I only see one variable. So my variable is sleep and is quantitative. So we're still looking at that same box for one mean. So we're still looking at one mean. That's the only thing we have. It has to be means because I'm talking about means. There's only one group, one sample. Okay. What would be your parameter? Your parameter is your population value. What are you going to use to summarize your population? So in this case, it makes sense to do the population average amount of sleep. And we don't know what that's going to be, so we'll just say it's mu. We don't know what the value is. But my statistic is my sample average. So X bar. And I'm saying average. That's out of habit from last time I taught it. Really, it's the sample mean. But I want you to remember it means average. Okay. My null hypothesis, well, let's write it in words and symbols. So the null hypothesis will be that the population average is what? Should we write less than 7 or equal 7? Remember, the null will always be equals. So the population average is 7 hours. Okay. Whereas the alternative then will be that the population average is less than 7 hours. So the alternative is always what you're hoping to show. The null is always kind of like dull, not interesting, and it's always an equal. And if you're going to write it in symbols, it'll be that your population mean equals 7, and your alternative will be that your population mean is less than 7. Again, remember, these are always about population parameters. It should never be about the samples. You shouldn't have X bars in there. Okay, it should be about the population parameters. Okay. So this is our theory-based applet, theory-based inference applet. Okay. We chose one mean. We put in our sample size, our sample mean, our sample SC. I click test of significance. I put in the 7, and I had to choose that it is less than, and click calculate. It will tell you different things like your standardized statistic. So if that my standardized statistic is t equals negative 2.57. This is the only one that we did in this class where we have a t distribution. The reason we use a t distribution is, remember, for means we had to use our sample mean and our sample standard deviation, and using our sample standard deviation introduces just a little bit more uncertainty. Our results are just a little bit more off. Okay, and so a t distribution just fits them just a little bit better than z distribution. It has just that little bit fatter tails. Okay, and so that's why this is a t. But if you look at the final exam formula sheet, okay, we don't have a different formula for how to find t. T would just be your statistic minus the mean of the null over SD of the null. It's the exact same formula. We just call it t, and we use a t curve. Okay. But t is just 2.57 and negative 2.57. And what does that mean? That means our statistic, which was our sample mean of 6.6, was 2.57 standard deviations below, because it was negative, the hypothesized value of 7. Okay, and so you can say, it could say the hypothesized value of 7 or the mean of the distribution. Okay. The mean of the null distribution. So they can say the mean of the null distribution, or you know that the mean of the null distribution, come back and look, what is the mean of the null distribution? It's mu, your population mean, which we're claiming is 7. Okay. What is the p-value? Our p-value is 0.0066. And if I was to interpret it, it's always the chance. So there is a 0.0066 chance of getting our sample statistic. So getting our sample mean of 6.6 or less. So that's our more extreme part. So 6.6 or less if the null is true. meaning if the population mean is 7. So that's how we'd interpret our p-value. You're like, oh, does that seem plausible? So there was only a 0.066 chance of getting our sample mean if the null is true. So does that null seem plausible anymore? I would say no. Okay, is it statistically significant? This just means your p-value is less than 0.05. So statistically significant is just a fancy word to say our p-value is less than 0.05. So yes, our results are statistically significant. Okay, do we have evidence? Well, our p-value is very small. In fact, it's less than 0.01. So we could say very strong evidence that the population mean is less than 7 hours. Okay. Remember, the alternative or the conclusion is always in terms of the alternative, because that's what we were hoping to show. That's always the answer we give our boss. And who can you generalize it to? So generalizing always comes back to, was it a random sample? So coming back up, it does say a random sample of students at that university. So I think I can extend it to all, we can generalize to all students at that university. Because the sample only came from that university, I can only generalize to students at that university, because other universities might be different. Maybe they have more homework at other universities. Okay. And if I wanted to find a 90% confidence interval for the parameter, that means my population mean. Okay, I just come back up to my theory-based inference applet. I put in 90%, and here is your confidence interval. So 6.33, or let's round a bit. So 6.34 to 6.86. So that means we can say something like, we are 95% confident that the mean sleeping time of all the students at the university is between 6.34 and 6.86. We don't know exactly what it is, but we're 95% confident that it should be between those two numbers. And again, we don't use the simulation approach for one mean because you have to have the entire population, so it just doesn't happen. So it'll all be theory-based for you on the test for the one mean.